Okay, how is everybody? Yeah? Any questions from last time or about the homework? Well, then we'll just keep marching on. So, what I want to talk about today builds on what we talked about last time. So let's recap. So if I give you a symmetric real matrix, we proved two things. One was that, well, remember that the eigenvectors and eigenvalues of a matrix, lambda and v, so lambda is the eigenvector, eigenvalue, v is the eigenvector. We saw that for symmetric real matrices, lambda is a real number. We proved that. So this statement is the same as saying, so if lambda is equal to its own complex conjugate, that means lambda is a real number. We also showed that if lambda 1 is not equal to lambda 2, then that implies that v1 and v2 have to be perpendicular to each other. They're orthogonal. Okay? Now it turns out, even if lambda 1 is equal to lambda 2, we can always choose eigenvectors that are orthogonal to each other. So, for example, if I give you the 2 by 2 identity matrix, the eigenvalue is 1. Okay, it's repeated twice. So you get an eigenvalue lambda 1 equals lambda 2 equals 1. Okay? And so this theorem does not require that the eigenvectors have to be orthogonal. And in fact, every vector is an eigenvector of this matrix because I take a vector and it has components w1, w2, and I multiply and I get w1, w2 back, pre-multiplied, say, by the number 1. So here I have the matrix times the vector equals 1 times the vector. So in this case, any vector is an eigenvector. And I can choose any two in the plane. This is a two-dimensional case. In the plane, I can choose any two independent vectors to be eigenvectors. But I could also choose them to be perpendicular to each other. So the point is, the theorem that we showed was that when lambda 1 is not equal to lambda 2, we necessarily get that these eigenvectors are perpendicular to each other. But the theorem does not address what happens if lambda 1 is equal to lambda 2. And so I'll just say, if lambda 1 is equal to lambda 2, we can choose v1 to be perpendicular to v2. So just like in the example over here, when you have repeated eigenvalues, in this case repeated as the number 1, we have many choices of what the eigenvectors can be, and it's convenient to choose the eigenvectors to be orthogonal in this case. Okay, so what is this useful for? Well, remember this is a class about dynamics, and we have seen many times when we write equations of motion. So for example, let's look at this one. Well, let's look at even a simpler one, just 2 degrees of freedom. If this is M, K, 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 and if this is x1 and x2, then the equations of motion, if we go through and write Lagrange's equations for this system, it looks like 2k minus k, 2k, x1, x2 is equal to 0. So this is, so we worked this out previously. We did it for k1, k2, k3. I'm just saying k1 equals k2 equals k3 equals k. But we get this kind of system where this is a symmetric matrix. In fact, this is easier than the general case because this is a multiple times the identity matrix, just the scalar m times the identity matrix, but it's still symmetric. And this is symmetric also. Right? What's above the diagonal and below the diagonal is the same. And this system, the equations of motion are linear to begin with, but if we start, for example, with the double pendulum, this is a case where the equations of motion will be nonlinear. So here the generalized coordinates are theta 1 and theta 2. The equations of motion will be nonlinear. There's going to be all kinds of theta 1 dots times theta 2 dots and theta 1 dots squared and all kinds of, and you have cosines and sines. It's just a big mess. But under the assumption that the angles are small, of course we have gravity pointing down in this case, under the assumptions that the angles are small and the rates of the angles, the theta 1 dots and theta 2 dots are small, we can linearize and put the equations, the linearized equations of motion in the same kind of form as that. Now, of course, the matrix K and the matrix M will be different in this case, but they will still be symmetric. And so this raises a very general question, and that is, if I give you equations of motion of this form, where M is symmetric and K is symmetric, how do we go about solving those equations of motion? Yeah?
That's supposed to be K theta.
Yes, no double dot on the second one. Thank you.
Sure.
Any other questions? Okay, so the general problem that we're going to address today is, so let's call this equation star. So if M is symmetric and K is symmetric, how do we solve star? Okay? And we're going to use these linear algebra facts over here. And we're going to use our knowledge of the solution for the one-dimensional problem. Basically, what we're going to do is use the linear algebra to decompose this system of equations, and we're generalizing here. This is, I drew two-dimensional examples, but we're going to generalize to the n-dimensional case and solve it in the n-dimensional case. Okay? And the way we're going to solve it is we're going to reduce the system of n equations, n scalar equations, which are all coupled to each other, because these matrices in general will be full. They will, in general, not have zeros off the diagonal. They'll look more like this matrix. And, but we can use these facts from linear algebra to decouple into a system of n equations, each in a single variable. Okay? But that requires that we redefine variables in sort of a clever way. And that's going to rely on the facts over there. So what I'd like to do is build on this idea a little bit. So, so this is all true, and we talked about it last time. And from these facts, if I tell you that we have A V1 equals lambda 1 V1, A V2 equals lambda 2 V2, all the way down to A Vn is equal to lambda n Vn, then, as I mentioned last time, we can put these together as A V1 through Vn. So we can take the eigenvectors and treat them as the columns of a matrix. And we can give that matrix a name. We can call it Q, for example. And then that, it has to be equal to the same matrix, V1 through Vn, times lambda 1 on the, through lambda n on the diagonal. So, right, so the first column just kicks off and you get a lambda 1 V1, and the first column here is A V1. So the first column corresponds to this equation, the second column corresponds to this equation, going all the way down to the nth equation. So what this equation says, if we're calling this Q, this is Q, let's call this right here capital lambda, which is the diagonal matrix that has lambda 1 through lambda n on the diagonal. So this says AQ equals Q lambda. But what we established last time was that Q is an orthogonal matrix. And we know from our discussion of rotations that an orthogonal matrix has as its inverse its own transpose. So if we multiply by Q transpose on both sides here, we get that A is equal to Q lambda Q transpose. Now this is a very convenient fact because it allows us to do things that we do with usual numbers. For example, I can talk about a function of A. So I could talk about what is the exponential of A. Okay? So I can talk about the sign of the matrix A. I can talk about the square root of the matrix A. You know, what are these things? Well, I'll tell you first what they are not. They are not just going to the entries of the matrix and computing those functions. Okay? So, for example, the exponential of the matrix A is not what you get by exponentiating A11, A2, A12, etc., and going through the matrix. Okay? That's what it's not. And likewise, the square root of a matrix is not what you get by just going through and taking the square root of each entry in the matrix. Okay? That can be a little bit confusing at first because when we talk about a constant times a matrix, that is going through and multiplying every entry in the matrix by a constant. Or when we talk about the derivative of a matrix, that is going through and taking the derivative of every entry of the matrix. But when we talk about functions of a matrix, it is not going through and performing that function on each entry. So what is it then? Well, the kind of functions that we're going to talk about have Taylor series. So for example, the exponential of a scalar x is, by its Taylor series, is 1 plus x plus 1/2 x squared plus 1 over 3 factorial. So this 1/2 is, you could view it as 2 factorial. 1 over 3 factorial x cubed the general term is going to be 1 over n factorial x to the n, but this goes out to infinity, this Taylor series. And when we talk about the exponential of a matrix, this is going to be replaced. Instead of the number 1, we have the identity matrix. Instead of the scalar x, we have the matrix A. Instead of 1 over 2 factorial scalar x squared, we have 1 over 2 factorial the matrix A times itself, which is A squared, etc. So we can define the matrix exponential to be defined by the Taylor series of the usual exponential function, except with the matrix put in place of the scalar x, and the identity matrix replacing the number 1. Okay? Now, the reason why this formula is very convenient, because if we substitute this in for A, and A squared, etc., well, let's see what happens when we take A times itself. So given this condition over here, A squared is going to be Q lambda Q transpose Q lambda Q transpose. Again, the parentheses are really not necessary since matrix multiplication is associative, so we can throw those away. We have a Q transpose Q. Since Q is orthogonal, though that cancels and we get Q lambda times lambda, that's Q lambda squared Q transpose. And it's not too difficult to see that no matter what power I raise this to, if I raise this to the nth power, what's going to happen is that we're always going to get a cancellation of a Q and a Q transpose, and this will be Q lambda to the nth power times Q transpose. Now, the reason why this is so convenient is because lambda is diagonal. If I take a diagonal matrix times itself, we'll just look at the two-dimensional case. This is going to be lambda 1 squared, 0, 0, lambda 2 squared. Okay? And if I took this to the nth power, this would just be raised to the nth power. Okay? So diagonal matrices are very special in this regard, in that they behave pretty much the way numbers behave. When I take this to a power, the power gets transmitted to the diagonal elements. Okay? It's not magic. I multiplied the matrices and I got that result. But that's not true for full matrices, matrices that don't have zeros off the diagonal. If I multiply, I get a mix of terms. So it's convenient that this is just each diagonal entry raised to the nth power. And then when I come over here to calculate my exponential, for example, what happens is, this is Q lambda Q transpose. This one is Q lambda squared Q transpose. The nth one is going to be Q lambda to the nth power Q transpose. And each of those terms has a Q on the left, and each of these terms has a Q transpose on the right, except for the identity. But the identity I could write, if I choose to, I could write it as QQ transpose, because QQ transpose is equal to the identity. And so what I can do is I can pull all the Q's out to the far left, and I can pull all the Q transposes out to the far right. And then what I have is the identity plus lambda plus 1 over 2 factorial lambda squared all the way out. Okay? The next term, of course, being 1 over 3 factorial lambda cubed, and the general one being 1 over n factorial lambda to the nth power. And the reason why this is useful is because this series in the middle here is we can look at it, the diagonal term by term, and what we get is that essentially the exponent, so this right here is the exponential of lambda, the thing in the middle. Now the exponential of lambda, though, because of what I just talked about with regard to the powers of lambda, can be written as e to the lambda 1, e to the lambda 2, down to e to the lambda n, and zeros on the diagonal. Now you say, wait a minute, you just told me that the definition of the exponential of a matrix is not the exponential of the entries of the matrix, right? That's what I said. Well, that's true because, even in this case, okay, because I did not take the exponential of the 1, 2 term, which was 0, right? That's still a 0 now. It didn't become a 1. E to the 0 is 1. If I were taking the exponential of every entry in this matrix, it's true that this would be e to the lambda 1, but then this would be a 1, and all of these off-diagonal terms would become 1s if I had been taking the exponential of the entries of the matrix. That's not what I did. I just took the exponential of the diagonal entries. And the reason why I can do that is because diagonal matrices act like real numbers when you go do things like exponentiation or defining a function. So it's easy to calculate the exponential of a diagonal matrix, and then the exponential of A is equal to Q times the exponential of lambda times Q transpose. So, in other words, if we do the eigenvalue-eigenvector decomposition of the matrix A, then we get the Q and we get the lambda. Then we exponentiate the lambda in the middle, and then we multiply by the Q and the Q transpose that we know to get the exponential of A. So it's kind of an involved process, except it's easier to do this than to add up an infinite number of terms. Right? If it's in the Taylor series, you really have an infinite number of terms. The fact that the thing in the middle here converges allows us to go to our calculator and calculate e to the lambda 1, e to the lambda 2, etc. So we have these values numerically on the diagonal, zeros everywhere else, and then we pre and post multiply by the Q and Q transpose respectively, and we can calculate our exponential of a matrix. Okay? Any questions about that? Well, you can define the Taylor series for the sine function. You can define the Taylor series for the cosine function. So you can calculate the cosine of a matrix or the sine of a matrix using a very similar procedure to what I did here. In fact, everything that I said with exponential could be replaced with any function that has a convergent Taylor series. So I could have, instead of saying x of lambda, I could have said f of lambda. And this would be f of lambda 1, f of lambda 2, down to f of lambda n. Now, this, though, does not have a convergent Taylor series. Okay? The square root function has a singularity at the origin. If you plot the square root function, it looks like this. So its derivative doesn't exist at 0, so it actually doesn't have a Taylor series. It doesn't have a convergent Taylor series. So the argument that I just said for this doesn't hold. However, we can handle this pretty easily in a very similar way using the same decomposition. If I tell you that I want to let B be a to the 1/2, whatever that means, we haven't defined it yet, then that means that b squared, which is just b times b, has to be equal to a. And if I tell you that A can be decomposed as Q lambda Q transpose, then a B that will satisfy that is Q lambda to the 1/2 power Q transpose. Because if I multiply B times B, the same thing that happened over there is going to happen over here. I'm going to get a Q lambda to the 1/2 times a lambda to the 1/2 times a Q transpose. But what do I mean by lambda to the 1/2 power? Well, I mean plus or minus the square root of lambda 1 down to plus or minus the square root of lambda n on the diagonal. Okay? So in fact, just like for a positive number, a real number, you can take a square root and you can have a positive square root and a negative square root. When you talk about the square root of an n by n matrix, there are actually 2 to the n power different possible square roots that you can get. Because there's 2 choices here, plus or minus. There's 2 choices the next place, all the way down to the nth diagonal element. There's 2 times 2 times 2 n times, so it's 2 to the n power possible square roots that you can get. Now, in what we're going to use the square root for, we only care about the positive square root. So then we go from 2 to the n choices down to no choice at all. We're going to define the square root of a matrix that has positive, a symmetric matrix that has positive eigenvalues. We're going to choose the square root to be the single matrix, which is, it has the positive square roots of all of the eigenvalues on the diagonal. Okay? And so, so we have an answer to our question. So, for example, if I give you this matrix right here, okay, let's let K equal 1 for simplicity. So I give you this matrix. So my matrix A is 2, -1, -1, 2. So what we're going to work out right now is what is e to the a and what is a to the 1/2 power. Okay? We're going to do an example. So the first thing that we need to do is calculate the eigenvalues and eigenvectors. And so how do we do that? Well, eigenvalues we get by calculating a characteristic equation. So that's going to be 2 minus lambda, -1, -1, 2 minus lambda. We take this determinant. So this gives us our characteristic polynomial. So the 2 by 2 determinant is easy to compute. It's just this times this minus this times this. So it's 2 minus lambda, quantity squared, minus 1 is equal to 0. So if we rearrange terms, this is lambda squared minus, this is going to be, well, I have to do FOIL here, 2 minus lambda times 2 minus lambda, right? So it's going to be lambda squared, there's going to be a plus 4, and then it's going to be minus -2 lambda, -2 lambda, so it's -4 lambda, plus 1 is equal to 0. Okay? So, and then this is a minus 1 here. So then the 4 minus 1 is 3. And this is a case where this factors. I don't even have to use the quadratic equation. So this is going to be a 3 and a 1, and they're both going to be minus signs, and if you multiply through, you get it, right? So we get lambda is either equal to +1 or +3. So that says that this A is what's called a positive definite matrix. It has positive eigenvalues. And when we take the square roots, okay, well, let's not do that yet. First, let's find our eigenvalues. First things first, our eigenvectors. So how do we find eigenvectors? Okay, well, we can come back to this same equation here, except we're not taking a determinant now. We're going to substitute in each eigenvalue, and then, so remember the eigenvector equation is lambda v equals, AV equals lambda v, which is the same thing as saying A minus lambda times the identity all times v is equal to 0. So once we know lambda, the condition that v needs to satisfy is that A minus lambda identity times v is equal to 0. So this right here is A minus lambda times the identity. So if we take each lambda and we substitute in, so let's put so this one is lambda 1 and this one is lambda 2. So if we put lambda 1 in, we get 2 minus 1 is 1, we get a negative 1, negative 1, 2 minus 1, we get a 1. So this has to multiply times the first eigenvector. We'll say it has entries v1, v2. Not to be confused with the vectors v1 and the vector v2. These are just the components of eigenvector 1. If you like, I can put a little 1 up here. The 1 and 2 component of eigenvector 1. That has to be equal to 0. Right? That this equation has to hold. And so when we do this, that says that v1 is equal to v2. Both of these equations say the same thing. They say that v1 is equal to v2. And remember, we are normalizing our eigenvectors so that they are unit vectors. So, if I initially choose v2 to be 1, that means v1 has to be 1. So the eigenvector, the whole eigenvector v1 would look like 1, 1, but that's not a unit vector. But we can then go and normalize it to become a unit vector, so we divide by square root of 2. Because 1 over square root of 2, quantity squared plus itself is equal to 1. So this is our first eigenvector, normalized to have unit length. And now let's see what happens when we substitute in lambda 2, which has a value of 3. That will make, now we're talking about the second eigenvalue. This is not a squared here. This is a superscript denoting that this is the second eigenvector. And when we put in a 3 instead of a 1, we get a 2 minus a 3. This becomes negative 1. This becomes a negative 1. And so in this case, what we get is that v1, 2 is equal to negative v2, 2. Right? So this equation is just saying that one of these is the negative of the other. And it doesn't matter which one is which. So in other words, we could choose v2 to be the number 1, and if we do that, then we get that v1 is the number negative 1, and that gives us our second eigenvector.